We are about to go over the Chapter 12 practice test in Sapling. I've copied these onto my whiteboard. You can also find these questions in page 846 through 848 in your textbook if you'd prefer to go through them that way. Question number 1. Recent revenue shortfalls in a Midwestern state led to a reduction in the state budget for higher education. To offset the reduction, the largest state university proposed a 25% tuition increase. It was determined that such an increase was needed simply to compensate for the lost support from the state. Separate random samples of 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors from the university were asked whether they were strongly opposed to the increase, given that it was a minimum increase necessary to maintain the university's budget at current levels. The results are given in the table. Our table below is talking about two categories. Basically, are you opposed, yes or no, and what is your grade level? So this is really a 2x4 table. The totals don't count in your row or column totals. Let's look at the question. Which null hypothesis would be appropriate for performing a chi-square test? In order to answer this question, first, you have to decide what chi-square test this would be. So we have 3 chi-squared tests. We have chi-squared goodness of fit. We have a chi-squared test of association or independence. And we have a chi-squared test for homogeneity. So it's goodness of fit if you have one category. So we're going to rule that out because we have freshmen, sophomores, juniors, and seniors, and a question yes or no. So it's not going to be goodness of fit because we have a 2x4. Association would be if it's one big survey and if they're independent or not. And since this is multiple surveys, it would not be association. So for that, we're looking for one survey. Here we have multiple surveys, separate random samples. So since we have multiple random samples, it's going to be homogeneity. And for those, we're trying to determine the distribution of each of these. So is the distribution of strongly opposed versus opposed similar in freshman, sophomore, junior, senior, or is it different? So that's what we're looking for our hypotheses. We're looking for homogeneity, multiple samples, and we're looking for distributions, not a relationship. So we're looking for that. So let's look at the question. Which would be the appropriate hypotheses? The mean number of students who are strongly opposed is the same for each of the 4 years. Year in school and student opinion about the student increase are independent in the sample. The distribution of student opinion about the proposed tuition increase is the same for each of the 4 years at this university. There is your answer. Null is there is no difference, whereas alternative is there is a difference. So the distribution is the same as no difference. That's your null. All right, question 2. Same scenario. The conditions for carrying out a chi-square test for homogeneity are independent random samples from the populations of interest, all sample sizes are less than 10% of the populations of interest, and all expected counts are at least 5. Which of the conditions are satisfied in this case? Well, we've actually satisfied the first 2, independent random samples and all sample sizes are less than 10%. We know we've satisfied this one because it's a university, so 50 students, 50 freshmen is going to be less than 10% of all freshmen and so forth. So 50 is less than 10% of each class. So we are good on the 10%, but we do have to figure out, are our expected counts at least 5? So I can do these by hand, or you can do them in your calculator. Let's do them in your calculator. So what we're going to do, clear my memory out here, is you're going to put them in a matrix. So do this with me. Hit the second x to the -1, go to edit. This is a 2x4 matrix. Enter your numbers in. You can press enter between each one. It should go in the direction mine are, just going from left to right. Only the raw data, don't put the totals. Next, click on your stat menu, go over to tests and go to chi-squared test. Not goodness of fit, just regular chi-squared. Keep your observed in A, your expected in B, go to calculate. There are your numbers, your chi-squared test statistic, your p-value, and your degree of freedom. If you needed those numbers, you could write them down. But we're going to go into our matrix menu and get our expected counts. So second x to the negative 1. As you can see, there's 1 in B now. Go down and click enter. And here are your expected counts. So we expect all the yeses to be 30.5, and we expect all the nos to be 19.5. Since they are all greater than or equal to 5, we've met all three conditions. So you can meet all, you've known all three conditions are met, we can do this test. Question number 3. All right, here's a different problem. A random sample of traffic tickets given to motorists in a large city is examined. The tickets are classified according to the race or ethnicity of the driver. The results are summarized in the table. We have white, black, Hispanic, or other. And here are your observed counts. Here are your proportion of city's population breakdown by percentages. So white, 55%, black, 30%, Hispanic, 8%, and other, 7%. So these are your stated proportions. And we want to know the racial ethnic distribution of traffic tickets in the city is the same as the racial ethnic distribution of the city's population. So it says, assuming the null is true, what is the expected number of Hispanic drivers who would receive the ticket? Well, we might as well get all of them because we're probably going to need them later on. So our observed is going to be 69, 52, 18, and 9. Our expected is going to be your percentages times your total. So you want to add these up here since it doesn't give you the total. Whatever the total is that's your sample size. So your total is going to be 69 plus 52 plus 18 plus 9. So add those together. There we go. So it's 148. So that's your sample size. So now we're going to take all of our proportions and multiply them by 148. So your expected counts will be this times 148. So we have 69, and then 69 times 148, or 69, I'm sorry, 148 times 0.55. And get that, and then you have 52, 18, and 9. We're going to do 148 times 0.3, 148 times 0.08, and 148 times 0.07. So let's get all of these, and then we can answer this question, but we can come back to these numbers because we'll need them. All right, 148 times 0.55, 0.3. It's important not to round these. Use your decimals when you're writing these out. So here are your 4 expected counts: 81.4, 44.4. 11.84 and 10.36. So Hispanic was the third one here. So our expected count for Hispanic would be 11.84. We'll come back to this table because we're going to run the test statistics. We're going to run the test itself with the numbers. All right, the next question. We wish to test the null, so we want to compute the value of the test statistic to be 6.57, assuming that the conditions are met, which of the following is the correct p-value. Now, if we're given the test statistic, we can actually go into chi-squared CDF. So I'll show you that one first since we're given that. So in chi-squared CDF, what you'll do is the lower is going to be the chi-squared. So the lower will be 6.57. Your upper will be infinity. So that's your 1e99. And then the degree of freedom is always going to be 1 less than the number of categories. So since there are 4 categories, then you'll do 4 minus 1, which would be 3. So let's get that first, and then we can get our p-value. So second bars, option 8, lower 6.57, upper 1e99, and the degree of freedom will be 3. And you get a p-value of 0.0869. 0.0869. So it will be between 0.05 and 0.1. So that's going to be your answer. Now, we will have to be able to get a chi-squared test statistic sometime without it being given to us. So what I do is I go to Stat, go to Edit, and in L1, put your observed. So we have actually our observed and expected. I'm going to go back to this one right here. So if you put your observed into L1, and in expected, you'll put in L2. So what we'll do is we'll run a chi-squared goodness of fit test. So stat, tests, D, chi-squared GOF. Observed in L1, expected in L2, DF would be 3. And we'll go ahead and calculate that. And you can see that p-value is 0.0868. You got your chi-squared test statistics, but more importantly, we have this thing called CNTRB, that's contributions. And we're going to use that in our next question. So the question is the category that contributes the largest component to the chi-square test statistic. So if you look at just the raw differences, the biggest difference, of course, is going to be between the whites, right? We have 69 versus 81.4. But that's not the biggest contribution to chi-squared, because remember that the chi-squared formula is observed minus expected squared divided by expected. So when we divide it by the expected, it actually is a smaller contribution overall than some of the other categories. So how you can do that, you can do it by hand. If you take the Hispanic, which was 11.84, and the expected was, or the expected was 8, the observed was 18, but the expected is 11.84. If you take that, subtract those differences, square them, and divide by the expected. Well, for Hispanic, it's going to be 18. That's your observed. Your expected is 11.84. If you square that result and divide it by 11.84, you will get that contribution to the chi-squared test statistic. So let's do that real quick. Now, if you look over here, you see this here, 1.888. That's the contribution from the white category. 1.3, that's the contribution from the Black category. 3.2, that's the contribution from the Hispanic category, and 0.178, that's the contribution from the other. So you can see the Hispanic did have the largest contribution at about 3.2. I'm going to back that up with this formula. So parentheses 18 minus 11.84, close it up, x squared, and then divide it by 11.84. There's your 3.2. That's the biggest contribution to the overall chi-squared test statistic, because remember the chi-squared is the sum of all of those. So Hispanic, but which one? Did Hispanic have 6.16 fewer tickets than expected or more tickets than expected? Well, this was actual observed. It had this number. It was more than what was expected. So we're going to click on this one here. Hispanic with 6.16 more tickets than expected. That's your biggest contribution. Question 6. For all chi-square distributions, p x squared greater than or equal to 1. 2, a chi-square distribution with fewer than 10 degrees of freedom is roughly symmetric. And 3, the more degrees of freedom a chi-squared distribution has, the larger the mean of the distribution. I guess I cut off part of the question, but basically, which one of these, or which of these should be true? That's always going to be true, because in a chi-squared model, it's going to be right skewed. And in a chi-squared model, any distribution, they're always going to, whether it's normal, t, whatever, those are always going to add to 1. So if you have, x is greater than or equal to 0, 0 is at the beginning, the probability of it being greater than or equal to 0 is everything under there. So it's going to be 1. A chi-square distribution with fewer than 10 degrees of freedom is roughly symmetric. Chi-squareds are always going to be right skewed. It doesn't matter the degree of freedom, it's going to be right skewed. So that is not going to be true. 3, the more degrees of freedom a chi-squared distribution has, the larger the mean. So a chi-squared with like 2 degrees of freedom might look like this. Chi-squared with 3 degrees of freedom is going to be more like that. And right, it's gonna get further and further be pulled to the right, but it'll still be right skewed. But the mean will get further out if that degree of freedom increases. So that's actually true. So it's going to be 1 and 3. Number 7, which of the following is not one of the conditions that must be satisfied in order to perform inference about the slope of a least squared regression line? Okay, so let's review those conditions really quick. I have them pulled up here from your lesson for day 3. There's an acronym that we want to use called LINER. Not to be confused with linear, but LINER, like Miss Liner. We have linear, which you want your data to look roughly linear. Independent, 10% condition. The normal is, that one's a little bit more confusing, but that just basically means, are your residuals normal? So are your y values normal for your x values? And then your equal standard deviation and random. And we'll go over those in a little bit. So for linear, let's talk about that real quick. You want to check whether your data looks roughly linear or your residual plot is randomly scattered. That's good. We don't want any curvature in the residual plot. That's not good. Independent, we want to be making sure that data is coming from, one doesn't affect the value of the other or less than 10% of the population. This is using a previous example in the lesson. The normal, this is where the residuals are normal for the y, so for the x value. So the y values are normal for the x values. And that is, if you can look at that a couple ways. You can look at a histogram and see if it's of the residuals and see if they're skewed or not skewed. Or your sample size is greater than or equal to 30, but that's very rare. So really looking for your residuals to be not super skewed or have any outliers. Equal standard deviation. That means that you don't want like more bigger residuals on one end than the other. So in this case here, you don't want it kind of funneling out. You want them to be roughly the same width all across in your residual plot. And then random, you just want your data to come from a randomized experiment or randomly assigned. So those are your conditions. So let's look at the question again. Which of the following is not one of the conditions? Data come from random sample. That is required, so we need that. The standard deviation of population of Y values corresponding to given value of X is always the same. That's your, regardless of specific value of X. So that's your equal standard deviation. You want that, so that's a good thing. For each value of X, the population of Y values is normally distributed. So you want your residuals. So for value of X, the population of Y values is normally distributed. You want your residuals to be normal. That's a good thing. So we're going to say that's a good condition. There exists a straight line such that for each value of X, the mean mu Y of the corresponding population of Y values lies on that straight line. Well, that's true. I mean, that's really just a linear condition more in detail, I guess. So that's a good thing. The last one, the sample size, that is the number of paired observations exceeds 30. That's not a requirement. As long as your residuals are normally distributed or roughly, or no super skewness or outliers, then we don't need that. So we really are, that's going to kind of replace that. So that's going to be your answer because that's the one that's not one of the conditions. We don't need it to be 30. All right, number 8, inference about slope beta of a least squares regression line is based on which of the following distributions? So slopes are, they're dealing with averages. So it's still going to be dealing with means. Means are t's, not chi-squared, not z's, not for normal, not chi-squared, not normal. It's t distributions, but because it's 2 variables, this is the only one where you have to subtract 2 from the number in the sample for your degree of freedom. So slopes are always t because t's are always dealing with means. And because this is 2 variables, you have to subtract 2 from the number of data points for your TCDF. All right, number 9 and 10 are dealing with the same scenario. So let's look at this question here. An old saying in golf is you drive for show and you putt through dough. Now, I don't golf, so I've never heard that. The point is that good putting is more important than long driving for shooting low scores and hence winning money. That makes sense. To see if this is the case, data from a random sample of 69 of the nearly 1,000 players in the PGA Tour World Money list are examined. The average number of putts per hole, fewer is better, and the players' total winnings for the previous season are recorded, and a least squares regression line was fitted to the data. Assume the conditions for inference about the slopes are met. Given is computer output from the regression analysis. And honestly, you'll probably be given all this number here, but just remember that the slope is going to be in this second line. So the constant, that's going to be like your y-intercept. And so this is going to be your slope. We're trying to predict so in these linear regressions, when we're doing inference, we're trying to predict the slope. So when you have a set of data, you get, y hat equals a plus bx. And this b is your slope, but it's not necessarily the true slope. It's a sample slope. And so what we're trying to predict is this theoretical ideal slope that exists. And that's what that beta is. Similar to how mu and x bar are related or p and p hat are related, it's beta in little lowercase b. So we have a hypothesis. The slope is 0. So the null is there is no slope. Basically, there's no relationship versus the slope is less than 0, which is there is a negative relationship. Which of the following is the test statistic? So this less than means it's one-sided. So if it were like not equal, it'd be two-sided, but this is one-sided, so we don't have to double anything. The test statistic, well, how do we get that? Basically, it's always going to be, if you think about the any test statistic, you take your statistic minus your null over your standard error. That's pretty much every test statistic, that your sample minus your null over your standard error. Well, we have our sample slope, right? It's negative 4,139,198. That's going to be this number here. That's going to be that lowercase b. Our null is 0. So we can put 0 there. And then your standard error, well, that's right here. That's this 1698371. You don't have to calculate that. That's going to be given to you. That's a kind of a complicated formula, and that's not a brain space we need to be using to figure out. So we're going to be given that, and our statistic here is going to be that negative 4139198. So since you're subtracting 0, it's going to be this negative 4139198 divided by 1698371. That's going to be your test statistic. So do that in your calculator, and then you can check with me. And that's going to be your T. Let's see what we get. So we get about negative 2.437. It's a negative because your sample slope is negative, so that makes sense. So negative 2.44. That's going to be this one right here. While we're at it, let me show you how to get the p-value. I'm not sure if the next question asks for that, but to get the p-value, since it's a one-sided test, you would go into TCDF. I'll show you. So second vars, TCDF, and your lower would be negative infinity since we have a negative t test statistic, so we want to go underneath it. We could put that negative 2.44 there, and your degree of freedom will be, depending on how many sample players, but we had 69 in the sample, so it'd be 67. 69 minus 2. So there, your p-value is about 0.00866. So if you were to be given that, it would be about 0.00866. And if it were a not equals, we would double that to get the p-value. And there it is right there. So here's our question, our second question related to that. There's the p-value given for you. So there's your 0.0087. And we want to know which of the following is a correct interpretation of this result. So first of all, p-value is less than whatever significance level. We'll say it's 0.05. So we would reject the null. Which means that we would conclude we have strong evidence to conclude that there is a negative slope. So but we're interpreting the p-value here. So the p-value in this case here is assuming the null, the probability of this sample to occur, or more extreme would be whatever that probability is. So assuming, or if there is no linear relationship, because the null is there is no linear relationship. So if there is no linear relationship between average number of putts per hole and total winnings for the players in the sample, the probability of getting a random sample of 69 players that yields a least squares regression line with a slope of negative 4,139,198 or less is 0.0087. Now, that's very similar to this. If there is no linear relationship between the average number of putts per hole and total winnings for the players in the PGA's Tour's World Money List, the probability of getting a random sample of 69 players that yields a least squares regression line with the slope of -4, 139, 198 or less is 0.0087. So it's going to be one of those two because that's how p-values are interpreted. The alpha would be the probability of making a type 1 error, not the p-value. So let's see which one's better. If there is no relationship between average number of putts per hole and total winnings for the players in the sample versus if there is no relationship between average number of putts per hole and total winnings for the players on the PGA Tour. Well, we're trying to make inference about a larger population. We're not just doing it for the players in the sample, we're doing it for everyone that we're trying to predict from. So the sample comes from that. So this is going to be the one you want. Last question. In an same scenario, the p-value of this test is 0.00087. Which of the following would make the p-value invalid? I think they missed the 0 in the last one, but that's okay. So which of the following make the p-value invalid? All right, if the scatter plot of the sample data wasn't perfectly linear, it's never going to be perfectly linear, so that's no good. If the earnings for the golfers with small putting averages was more variable than the earnings for golfers with large putting averages. So that'd be like if you had, let's say, small putting averages, the earnings for the small was more variable, so you got a higher numbers here, and then you got large putting averages, small numbers there, and maybe in the middle it kind of goes up. That's not good, right? That's invalidating the equal standard deviations rule. Equal standard deviations mean we don't want kind of something like that going on with your residuals. So that's going to be your answer. That's going to invalidate all this numbers. Look at the other ones. If the standard deviation earnings is much larger than the standard deviations of the putting average. So if the Y value standard deviations are bigger than the X values, that's not a big deal as long as they're consistent throughout. So that's not going to work. If the distribution earnings has an outlier, you can have an outlier in your earnings. If the distribution of earnings wasn't approximately normal, your earnings doesn't have to be normal for this to work. You just don't want to have strong skewness of your residuals. So it's really going to be this one here. The earnings for the golfers with small putting averages was more variable than the earnings with large putting averages. That's going to be the one. Hopefully that made some sense. I know this stuff's kind of tricky, especially when you don't have a lot of time to practice with it, but thank you for watching.